Have a nice time. In this video, you will be introduced to quadratic forms and transformation of quadratic forms to principal axis. Let us start with some basic definitions. A real square matrix capital A is called symmetric if its transpose equal to the matrix itself, that is A transpose equal to A. It is Q symmetric if A transpose equal to minus A, and it is called orthogonal if A transpose equal to A inverse. And another definition, orthogonal transformations. Orthogonal transformations are transformations of the form y equal to ax, where A is an orthogonal matrix, that is A inverse equal to A transpose. So we are taking such a matrix A and y equal to ax becomes an orthogonal transformation. For example, let x be an element in Rn. So if n equal to 2, you may consider this example. X is the vector x1, x2. And let capital A be the matrix cos theta minus sin theta, cos theta. Actually, this is an orthogonal matrix because here A inverse equal to 1 by determinant is here cos square theta minus of minus, that is plus sin square theta, into the matrix. We will interchange the elements in the main diagonal. So again it is cos theta itself, and here we will change the sign. So sin theta, here it is minus sin theta. So this is A inverse, and this is actually equal to 1 by 1 into cos theta sin theta minus sin theta cos theta. And we may verify that it is equal to A transpose. A transpose means you are interchanging the rows and columns of this matrix. So first column becomes cos theta minus sin theta, and second column sin theta cos theta. So here A inverse equal to A transpose. So here capital A is an orthogonal matrix. So you consider the transformation y equal to ax, that is y equal to the vector y1, y2, that's equal to the matrix A into the matrix x. Such transformation is called an orthogonal transformation. Now we recurse to important results. Orthonormality of column and row vectors. A real square matrix is orthogonal if and only if its column vectors a1, a2, etc. an form an orthonormal system. What do you mean by an orthonormal system? Consider the vectors a1, a2, etc. an. If you take any two distinct vectors, then the dot product becomes 0. That is aj dot ak equal to 0. If j not equal to k, you are taking two distinct vectors from the set, then the dot product becomes 0. And if j equal to k, then the dot product becomes 1. That is a1 dot a1 equal to 1, a2 dot a2 equal to 1, etc. So such a system is called an orthonormal system. And the result says that a real square matrix A is orthogonal if and only if its column vectors form an orthonormal set. So we have a matrix capital A, and suppose the matrix is equal to A1, A2, etc. an. So actually here A1 represents the first column of the matrix, A2 represents the second column, etc. And suppose this set A1, A2, etc. an forms an orthonormal system. Then according to this result, A becomes an orthogonal matrix. That is A inverse equal to A transpose. If the column vectors of a matrix form an orthonormal system, then capital A is orthogonal. Conversely, if A is orthogonal, then the column vectors becomes an orthonormal system. That is the first result. And second result says, a symmetric matrix has an orthonormal set of linearly independent eigenvectors. Suppose capital A is a symmetric matrix. Symmetric means A transpose equal to A itself. Suppose you have a matrix like this. Then if you find the eigenvectors of this matrix capital A, or if you find the basis of eigenvectors, linearly independent eigenvectors, then it forms an orthonormal set of vectors. So we will be using these two results in our coming discussions. Now let me explain what you meant by a quadratic form. A quadratic form Q with the components x1, x2, etc. xn of a vector x is a sum of n squared terms, namely q equal to x transpose ax. So in a quadratic form with n components, x1, x2, etc. xn, there will be terms with x1 square, then x1, x2, etc. x1, xn. Also terms with x2, x1, x2 square, etc. x2, xn. And likewise there will be terms with xn, x1, xn, x2, etc. xn square. Here the matrix capital A is called the coefficient matrix of the quadratic form. And we may assume that this matrix A is symmetric. Why? For example, consider this quadratic form x transpose Ax. Here we are considering a 2 by 2 matrix A. So capital X becomes x1, x2, and you have x transpose Ax equal to the row vector x1, x2 into the matrix A into the column vector x1, x2. When you multiply all these matrices, you will get an expression like this. It's equal to 3x1 square plus 10x1, x2 plus 2x2 square. And suppose you are taking another matrix here in the place of A. So you have x transpose Cx equal to, in the place of 3, 4, 6, 2, here you have 3, 5, 5, 2. So the speciality of this matrix is actually symmetric. So if you take the main diagonal, the other elements are symmetric with respect to the main diagonal. So when you consider this matrix, then the quadratic form is actually equal to the previous one. Hence, given any quadratic form, we can consider the matrix corresponding to the quadratic form as symmetric. For example, if you have a quadratic form 2x1 square plus 14x1 x2 plus 3x2 square, then corresponding matrix you may taken as 2, 3 here. Main diagonal becomes the coefficients of x1 square and x2 square. Then here it is 14. So 14 divided by 2 is 7. So you take here as 7 and 7. So the matrix 2, 7, 7, 3 becomes the matrix corresponding to this quadratic form. So given any quadratic form, there may be many matrices corresponding to that one, but you may assume that the matrix corresponding to the quadratic form is symmetric. Now consider the quadratic form Q equal to x transpose Ax. Since A can be assumed as symmetric, it has an orthonormal set of linearly independent eigenvectors. By a previous theorem, we just stated, since A is symmetric, it has an orthonormal set of linearly independent eigenvectors. So you construct a matrix capital X having columns as these eigenvectors. Then by another theorem, you have X is an orthogonal matrix. Just remember about the theorem again. If A is a real square matrix, then orthogonal. It is orthogonal if and only if its column vectors forms an orthonormal system. Here capital A has an orthonormal set of linearly independent eigenvectors. Therefore capital X is having columns that eigenvectors. So X is an orthogonal matrix. Orthogonal matrix means X transpose equal to X inverse. Now remember, capital A is a matrix and capital X is a matrix with columns as the eigenvectors of A. So you know the result. X inverse Ax must be a diagonal matrix having the diagonal elements having the eigenvalues of capital A. Okay. Likewise, you may write here X inverse Ax equal to D, where D is a diagonal matrix having the diagonal elements as the eigenvalues of A. Now you multiply this expression X to the left side and X inverse to the right side, both to the LHS and RHS. We get X into X inverse becomes the identity matrix. Here again X inverse becomes the identity matrix. Now in the left hand side there remains capital A and the right hand side becomes X into D into X inverse. So now we have the expression A equal to X D X inverse, and we know X inverse equal to X transpose because capital X is orthogonal. So in place of X inverse you may write X transpose here. Our given quadratic form was Q equal to X transpose A into X. Please don't confuse with the small x and capital X here. Capital X is a matrix with columns as the eigenvectors of capital A, and small x is only a vector, column vector, x1, x2, etc., xn. Okay, so q equal to x transpose ax. So in the place of a, you may substitute this one, xd x transpose, and we can combine this x transpose into x together. Here also x transpose into capital X transpose into small x together, and put this x transpose capital X as y. So what will be y transpose? You have x transpose small x whole transpose. So this is of the form A into B whole transpose. So the formula is B transpose into A transpose. So you have small x transpose into capital X transpose transpose, that is capital X. So that is actually here appears x transpose into capital X. So if you put y here, this one is y transpose. So this expression becomes q equal to capital Y transpose into D into Y. Since D is a diagonal matrix with diagonal entries as the eigenvalues of capital A, this expression becomes, and all other elements here are zeros. So this expression becomes lambda 1 y1 square plus lambda 2 y2 square plus etc. plus lambda n yn square. So from the given quadratic form, q equal to small x transpose capital A x, we transformed this quadratic form to this form in which there is only the square terms of the variables. And this form is known as the principal form or canonical form of the given quadratic form. So you have to remember the formula here, y equal to x transpose into small x, then q equal to y transpose into dy. What kind of conic section is given by the quadratic form? Q equal to 3x1 square plus 8x1x2 minus 3x2 square equal to 10. Transform it to principal axis and express the vector x1, x2 in terms of new coordinate vector y1, y2. This is a problem. So first of all, you have to identify the symmetric matrix corresponding to this quadratic form. So the matrix A equal to 3, 4, 4, minus 3. Here 3 minus 3 are the coefficients of x1 square and x2 square, and here the 4, 4 are obtained by taking the half of this one. 8 by 2 is 4. So you place 4 and 4 here. Thus you can find the symmetric matrix A corresponding to the quadratic form on the LHS of this equation. Now we have to find the eigenvalues of capital A. It is given by determinant of A minus lambda I equal to 0. That is determinant of 3 minus lambda 4, 4 minus 3 minus lambda equal to 0. And forming the corresponding equation and solving, you may get lambda square equal to 25 or lambda equal to plus or minus 5. These are the eigenvalues of the matrix A. Therefore, the principal form or canonical form of the LHS of the expression is 5y1 square minus 5y2 square equal to 10. In the place of this quadratic form, we substituted the principal form or the canonical form, and that's equal to 10. So cancelling 5, we have y1 square minus y2 square equal to 2. And you know this represents a hyperbola. So we identified the conic represented by this quadratic form. Now we have to express the vector x1, x2 in terms of y1, y2. For that, we have to find the characteristic vectors corresponding to lambda equal to 5 and lambda equal to minus 5. When we put lambda equal to 5, then consider the equation a minus 5y into x equal to 0. And you know how to find the corresponding characteristic vector. We reduce the matrix to the row canonical form. And the corresponding equation becomes x1 minus 2x2 equal to 0. Put x2 equal to some t parameter. Then x1 equal to 2t. So corresponding vector is x1 is equal to 2, 1. If you put t equal to 1 here. And we have to normalize the vector now. Normalizing the vector means you have to divide each element of the vector by the norm of the vector. What's the norm here? It is square root of 2 square plus 1 square. That's equal to root 5. So you divide each element of the vector by root 5. So the normalized vector is x1 dash equal to 2 by root 5, 1 by root 5. So in this way, you have to find the characteristic vector corresponding to lambda equal to minus 5 also. Now consider lambda equal to minus 5. So you have a plus 5i x equal to 0. And this is a matrix equation. And we reduce the matrix to the row canonical form. Corresponding equation is x1 plus 1 by 2 x2 equal to 0. Put x2 equal to t. Then x1 becomes minus 1 by 2 t. So considering t as 2 here, then the corresponding characteristic vector is minus 1, 2. Okay, and we have to normalize the vector now. What's the norm of the vector here? Square root of minus 1 square plus 2 square. This is again root 5. So the normalized vector is x2 dash is minus 1 by root 5, 2 by root 5. And you may note that x1 dash and x2 dash are the normalized vectors now. And these are orthogonal because 2 root 5 into minus 1 root 5, that is minus 2 root 5 plus 2 root 5 becomes 0. So the vectors here are orthogonal. And we construct the matrix X as the column vectors x1 dash x2 dash, that is x is equal to 2 by root 5, 1 by root 5. It's the first column. Second column is minus 1 by root 5, 2 by root 5. Thus we constructed capital X. Now you have to find y. Y equal to x transpose into small x. So capital Y equal to x transpose into small x. This equal to, write the transpose of the matrix. That is the first row becomes 2 by root 5, 1 by root 5. The first column becomes the first row. Second row becomes minus 1 by root 5, 2 by root 5. So this is capital X transpose. Now small x is x1, x2. Okay, we will find y1, y2. So the equation becomes y1 is equal to 2 by root 5 x1 plus 1 by root 5 x2. And y2 equal to minus 1 by root 5 x1 plus 2 by root 5 x2. So this is a formula to change the given axis to the principal axis.